Yes, I do. Blame you. Okay, so here we go. Who can tell me the amplitude? 4. There is no negative amplitude. It's just 4. It's the number in the beginning. Period. You may remember that it's of the form 2 pi over b. Yeah, 2 pi over b. What's my b value? 1/3. 2 pi over 1/3 gives you a period of 6 pi. Phase shift. Who can tell me the formula for phase shift? Negative c over b. Well, I think it was actually just c over b. Just remember. So that's negative pi over 1/3, which is negative 3 pi. Thank you. Vertical shifts. Negative 3. You are going to be required to know those things on the next test. You always take the opposite of the sign. So because that's positive, the phase shift was negative, and it's just c over b.
Wait, so
C over pi over 1/3 reduces to 3 pi.
pi over 1/3, wouldn't that be pi over 2?
No. Pi over 1/3 would flip and be pi times 3. Flip and multiply.
Oh, because 1/3 is 2?
Yes.
Oh, okay. See, that's what I was understanding.
Well, it sounds like you got it now. How we got negative 3 pi? C over b. Negative pi over 1/3. So that's the same as negative pi times 3 over 1, negative 3 pi. Whenever you divide by a fraction, it's basically going to make your number bigger every time. 2 pi over b for your phase shift. That's the formula. 2 pi divided by 1/3. Once again, divided by a fraction makes it bigger. Nope. Well, theta is just like x. It's just the variable. Any other questions from the Dom? What? That's all. You always flip this sign. Okay. Remember horizontal shifts back in normal graphs? If it was +2, it actually went left 2. If it was -2, same difference. Okay. First form you need to write down today. This is essentially the only thing you need right here. This part right down here at the bottom, and I'll explain in a second. 6.7. 6.7. Yes, the dot product. Vector v dot vector w renders you that dot product. Okay. The A's are the coefficients on the I's, and the B's are the coefficients on the J's. What? You saying?
And so the whole thing is just
I would just write the part at the bottom. The rest of it will be pretty self-explanatory. Dot product is going to help us do some things today. The dot product is very similar to the determinant for matrices. It kind of serves purposes that help us conclude things about the actual matrix. It won't really do something all by itself. Everybody got that written down? Only part you really need is the apple. This one right here. Right? The apple formula. All right. You're welcome. Okay. So, first thing you're going to do is literally you're just going to find some dot products. We're going to find v dot w and v dot v. V dot w. So you just multiply the coefficients. 3 times 1 plus 1 times 3. So the dot product of VW on number 1 is 6. You also need to do v dot v, but I'm going to do a few more v dot w's just because it's easier to see. Yep. Number 5. If we did v dot w on number 5, negative 6 times negative 10 is 60, plus negative 5 times negative 8 is 40, which gives you a dot product of 100. Yes. Number 7. What is the I value on W down here? 0. So 5 times 0. And then 0 times 1. And that just gives you a dot product of 0. Oh, okay. Let's do like V times V on number 5. So you just have to remember, basically you're just going to square both of these, because you're just multiplying it by itself. Negative 6 times negative 6 is 36. Negative 5 times negative 5 is 25. So the dot product of V dot V on number 5 would be 61. Yes? I'm going to get to that. Like I said, much like the determinant in matrices, by themselves they serve no purpose, but you can use them to make other conclusions. One of the conclusions we're going to get to a little later is, one thing we're going to do is, we are going to be looking at vectors and being able to determine the angle between vectors. Now, in this class, we're pretty much always dealing with two-dimensional vectors, x and y. But they can come off in any direction. They can be x, y, z vectors and go off in, any. And you don't, in 2 dimensions, you can have parallel, you can have perpendicular. In 3 dimensions, there is no perpendicular. There's orthogonal. Orthogonal in 3 dimensions basically means that 2 vectors are perpendicular. That's essentially what it means. But like, instead of always being like this, these would also be orthogonal. Or so with these, and these, and these. And it really, so there are so many ways the vectors can be perpendicular in 3 or more dimensions that they use a bigger word, orthogonal. And the only reason I'm telling you this is the dot product. One of the things that's going to help you know, if you get a dot product of 0 with 2 vectors, those vectors are orthogonal with each other. And one of the things I'm going to be asking you to do a little later is, I'm going to say, here's 2 vectors. Find the angle formed between those vectors when they cross. Well, if you know that their dot product is 0, you can just jump the gun and say, oh, they're orthogonal, perpendicular, and therefore their angle between them is 90 degrees. So that's one thing you can use it for. If you get 0, you immediately know that they're perpendicular or orthogonal. Any other questions from this slide? We're going to get to that. All right. Here's just putting dot products with some stuff we did yesterday. It's just order of operations. So like, somebody pick one you want to see. 13. 4u would be 8i minus 4j. V would be 3i plus j. And then finding the dot of that, 24 minus 4 would be 20. Is there another one somebody wants to see? Yes. Find the finished number. Something else somebody wants to see? 11. U dot V, well, that's 2 times 3 is 6. Negative 1 plus 1 is negative 1. 6 minus 1 is 5. Plus UW, 2 times 1 is 2. Negative 1 times 4 is negative 4. 2 minus 4 is negative 2. So 5 plus negative 2 equals 3. Now you can show more or less work however you want to. Because the dot product doesn't do that. It just gets like one number. It's similar to the determinant in the matrix. Remember how that was just one number? Very, very similar. Well, UV is a dot product, so it's just going to be a number. And then you just take that number and multiply it by 4. Like UV, I think we already found was 5 up on this one. So that'd be 4 times 5. So 15 would just be 20. Other questions? No? Alright, let's just keep moving. We're already half done. Second thing you need to write down, I would really focus on this formula, the right-hand formula. The left-hand formula is good too, but the right-hand formula basically just goes one further step, and that's essentially what you're going to need today. To find the angle between 2 vectors, to find the angle formed by 2 vectors, you can use that formula. their dot product over their magnitude product. Their dots over their mags. Cosine inverse of dots over mags. Everybody got that written down? Now, if you're somebody who likes to know where the formulas come from, I believe there's a pretty good explanation in the book, but I thought I'd spare you guys. But if you want to, it's there. Got this written. Now, please notice, when you start looking for the angle between two vectors, it's going to be tempting to just jump straight in and find their magnitudes first. That way, you don't have to come back and do that after you find their dot product. But you want to start with the dot product, because if the dot product is 0, exactly, so there's no point in doing anything else. If you get a dot product of 0, the answer is 90 degrees every time, because cosine inverse of 0 is 90 degrees. And you shouldn't have a magnitude of 0, or you wouldn't even have a vector. That's impossible. So don't worry about getting 0 in the denominator. Okay, here we go. Find the angle between V and W. First thing I'm going to do is find the dot product. So 17. Darn, I'm still in Apple mode. 2 times 3 is 6. Negative 1, thank you. Plus 4 is, or excuse me, times 4 is negative 4. So my dot product is 2. So I'm going to be doing cosine inverse of 2 over, now I need the magnitudes. What's the magnitude of this one after Pythagorean theorem? I know some of you guys are pretty quick at this. A squared plus B squared, square root of 5. What's the magnitude of this guy? 5. So this is going to be square root of 5 times 5. And you don't have to rationalize that, you're just putting it in the calculator. So, and we're going to be in degrees all day today. Go. Alright, so make sure I'm in degree mode. Cosine inverse of 2 divided by quantity. You need to make sure to put the whole denominator in quantity. 5 times the square root of 5. Close all my parentheses. Enter. So to the nearest degree, what is that, about 80 degrees? So the answer to this one would be 80 degrees. That is the angle formed by those two vectors. Excuse me? That's finished. That is the angle between them. Yes, for these two, yes. I'll take a little bit more time. Let's look at 21. Because this one's just 5. Yeah. Alright, dot product of 21. 6 times 5 is 30. Plus you. 0 times 4 is 0. 30 plus 0. So this one has a dot product of 0. I'm going to come back to that. Magnitude. What's the magnitude of the first one? What did I say? I meant 30. I apologize. What's the dot product? Yeah, dot product is, or excuse me, the magnitude of V is 6. Uh-oh, I think we jinxed it. What's the magnitude of W? A squared, B squared, 41? Square root of 41? Excellent. Let me actually show that. I'm probably skipping a few things. Come on, Pen. You've been doing well. Who's bragging on you? Alright, to find the magnitude of W, A squared plus B squared equals C squared. 25 plus 16 equals C squared. 41 square root. So that's where these are coming from. So, we're ready for our formula. Cosine inverse of dot product over magnitude product. Now, yes, you can reduce this if you want to. It's a 5 over 1. But it's up to you. Since you're just putting it in the calculator, I guess you don't have to do that. Although it would be easier putting it into the calculator if you did do that. Yeah, so it would just be 5 over radical 41. So cosine inverse 5 divided by radical 41, 39 degrees. Muy goodo. Questions about that one? If you're doing one of these and you get a 0 dot product, just stop and put 90. Well, you could finish it, but you're going to get 90. So just, I would stop. Exactly. Wasting time. Not good. Don't beat yourself up, but yes, you do. Okay. Other questions from this slide? Awesome. Let's just keep going. Only 2 slides left, and one of them is the assignment. So this is the last slide. Use the dot product to determine whether they're orthogonal. Now, it didn't ask you for the angle. So all it wants you to do is find the dot product and just say are or are not orthogonal, which basically means perpendicular. So 23. What's going to be my dot product? 1 times 1 plus 1 times negative 1. Is it orthogonal? Yes. Or yes. Only time. Only time. And also, anytime you get one. Am I missing something here? Whatever. Oh, I see this. Oh, these are. Anytime you get 2 with just I, now they may not be going in the same direction, but they're going to be like this. And you can pretty much know they're not going to be orthogonal. Or if they were both J, they're not going to be orthogonal. But anytime you get one with just I and the other one with just J, you know one of them is horizontal, one of them is vertical. Are they going to be orthogonal? Yes, every time. Anytime you only have one letter in both of them and they're directly opposite, they're going to be orthogonal. Anytime you have the same letter, they won't be. But you still have to do all this in the end. Yep. That just changes the direction. It doesn't change the angle. Direction has no bearing on angle. Yeah. They don't. Good question. All of these are going to start at the origin. That's an excellent question. But in this section, we are assuming that they all start at the origin, therefore have that common start. Not orthogonal. Right, not orthogonal. This one, yes. You can do this yes, no, I guess, if you wanted to. Questions? Okay. Dang. Only have 70 minutes to get it done. There you go. Toward the end, if we